Sharov. He's from Boston University, and his talk is An ARCIS Study of Io's Aurora in Jupiter's Shadow. So go ahead, Mikhail, and you can start sharing.
I hope you guys can hear me.
Yep.
Perfect. All right, so today I'm going to be talking to you guys about, as you said, an ARCIS study of Io's aurora in Jupiter's shadow. So we use the 3.5 meter Echelle telescope, or the 3.5 meter telescope with the Echelle spectrograph to look at Io's tenuous atmosphere as it goes in and out of eclipse. So this is an interesting sort of study because Io's atmosphere is super sensitive to temperature, Io plasma torus interactions, etc. So we really want to know what's going on with the atmosphere, and the eclipse is a good way to determine how it forms and what supports it. So we find that both NAD and oxygen 6300 angstroms, so that's red line oxygen, behave differently during ingress and egress from the eclipse. And this is most likely we attribute it to differing pathways for their production. And as you can see on the right here, there's a little image of the slit of ARCIS covering the Io disk as it comes out of eclipse from Jupiter's shadow. Okay, so one thing that's sort of important here is the observation method, and that's the non-cycle blind tracking. So this is really difficult to do because, first of all, it's non-sidereal, so we have to directly point the telescope or tell the telescope where to go. And also, it's a completely dark object, so maybe it comes through on the computer, maybe not. On C, there's still a little bit of glow from the penumbra, but on D, it's pretty much completely gone, so we're just guessing that we're pointing in the right direction. Io's disk is only 1.1 arc seconds in width, and the slit is 1.6 arc seconds, so it's really, really easy to drift out of that region. And that sort of gives us issue with determining temporal brightness, because if we drift out of the slit, we're obviously going to get less bright results. But we have a way to deal with that. And one of those ways is to double check the pointing. We do this through guider images and emphoresis, the red and yellow on the plot. We have a coordinate system in the FITS header, and we roughly check this. So roughly is the key word here. We're not entirely sure if we're constantly pointing at Io all the time. And there are small errors both in the refraction model at APO, basically where the telescope is supposed to be pointed. And also, as seeing throughout a night gets worse and worse, we're obviously going to take a hit in like where we're pointing or the brightness that we're seeing. So temporal effects can sometimes be a little bit difficult to track, but we have ways of dealing with this, which I'll talk about later. So the data reduction is done through PyRef and the ARCIS pipeline, thanks to Gene McKeever. And we correct the tellurics, especially at oxygen 6300, using an A0B star. These plots show some of these waterfalls, the cascading sort of temporal effect, where the earliest ones are dark red and the latest ones are dark blue, so it actually goes up in this case. So the background is obviously mostly Jupiter, and all of that is subtracted using an image of Jupiter's disk as a standard candle, because we know the absolute flux calibration and everything. And for NAD and red line oxygen, so that's 6300, we use those because they have been found to be the brightest emissions at Io, and they were both detected but not characterized by Boucher et al. 2000, which means we know that they're there, but we don't really know what's going on. And that's what this study looks to sort of talk about. And these are some of the main results. We can see on the left side of the plot, it's a brightness versus, or time versus brightness. And we can see that electron excited sodium collapses, that's the yellow here. And the blue is actually a concurrent on the same date ALMA observation of sulfur dioxide and sulfur monoxide by De Peter. And we can see that that's the bulk atmosphere, and it's definitely collapsing there. But the inflection, or the slope of sodium, looks to be even more gradiated, so it could be collapsing even faster. And like I said, the temporal trends are not entirely to be trusted, But one way we can sort of back this up is through the NAD2 to D1 ratio, because no matter how much sodium light we're actually getting, that ratio will always be the same. So the ratio actually corresponds to how optically thick the atmosphere is, or specifically the sodium atmosphere. So since we go from optically thick here to optically thin here, we know that the atmosphere is in fact changing and it's not just Io slipping out of the slit. And because sulfur dioxide is actually thought to be a producer of oxygen, we would expect that oxygen would also decrease as sulfur dioxide and sulfur monoxide does. However, as you can see here, we actually have a really funny trend where oxygen is increasing post ingress into eclipse. So what's going on with that? We find that oxygen actually correlates or anti-correlates, I suppose, with a negative trend to the latitude of the torus geometry. So as Io gets closer to the center, or the centrifugal equator of the torus, it gets brighter, and as it goes further, it gets darker. Sodium, on the other hand, does not exhibit such behavior. There's no real correlation here that can be found, but here it's very clear that it's sort of a negative trend. And also, because oxygen has a radiative lifetime of 2 minutes, it actually acts as a good proxy for incident plasma density. And that's how we can sort of explain why oxygen has this sort of completely weird behavior going into eclipse. Another thing we studied is the sodium recovery at ingress. So if you expect sodium to sort of collapse, you would also similarly, I guess, expect it to puff back up once sunlight comes in. That's not entirely what we see, and there aren't any conclusive results that we can sort of say that sodium collapse and recovery happen at different timescales. There's definitely something interesting going on here, and I'll attempt to explain these plots here. So the blue line here is we take a column density. So in this case, it's somewhat arbitrary. It's just what we took to be somewhat good fitting to the line. And that's 1.1 times 10 to the 12th of a column density. So that's if it was fixed. And this is basically, this growing effect is just due to the geometry and velocities of Io coming out of eclipse. However, we can see that our real data here, it's slightly more gradiated. It's sort of hard to see, but one thing that backs that up is that once again, we look at that D2 to D1 ratio. We can see that it starts off optically thin, so that really high ratio, and then it also collapses, meaning it gets optically thick again. So we can tell that there is definitely something going on with the atmosphere. Whether or not that's enough to really say that there's a different time scale or that it's completely puffing back up again, that still needs a little bit more work done on it, but we're definitely seeing some interesting effects here. So as sort of a concluding remark on our results, so using that 3.5 meter telescope, we found all this new behavior that's completely unexpected in a lot of cases, such as oxygen and sodium here collapsing. So despite the bulk atmosphere collapsing, oxygen once again doesn't, and it seems completely non-responsive. So here, one of these trends, the APO one, it definitely seems like it's following the trend, but then this observation at LBT completely throws that out because it's increasing. And because this is going from optically thin to optically thick, the sodium trends here would actually be more increased, so it would be even less correlation here. So, and that non-responsive oxygen, because it doesn't seem to be affected by eclipse, whereas sulfur dioxide does, means that that production pipeline from sodium dioxide and sulfur dioxide and sulfur monoxide must be pretty slow, at least on timescales of an hour, because that sort of production isn't catching up with the torus, meaning that it's the effect is sub that of the toroidal geometry. So another unforeseen thing that we find is that sodium experiences that rapid depletion in eclipse and changes from optically thick to optically thin. That definitely means that the atmosphere is changing. Whether or not it's actually completely collapsing or not, we still are not entirely sure. And once again, that optically thick to optically thin would even exaggerate that trend because we're actually seeing less signal here, or less signal here than we should. So we interpret that response as an interruption of the production channel from NaCl+, so that's an ion with rapid supply and loss. And this probably depends on sunlight. The reason we say this, and it's not, for example, sodium being neutral or something like sputtering occurring, is because we see that the bulk atmosphere collapses. So in theory, that should make sputtering even easier based on the plasma torus. So if the atmosphere is thinner, more stuff will get to the sputtering sodium on the surface, but that's not what we see. We see it still collapses. There are a couple of other reasons why we believe that this is sodium chloride, and it must depend on the sunlight. But I see that I'm running out of time here a little bit, so I can answer that in questions or wherever. And one thing you may have noticed is that we have a lot more in the data set here compared to just this first plot. That stuff is somewhat in ingress and further into Eclipse, and we're still getting it ready for analysis and sort of to produce any meaningful results out of it, especially with the pointing, which we can't entirely confirm, and therefore the temporal results are somewhat dodgy at best. So, but we have possible other results of the first detection of potassium, sort of this red line to green line oxygen ratio, and basically a lot more cool stuff is going to come out of this data set from APO with ARSs. And that's about it. I'll be taking questions. Thank you.
All right, thank you. So, okay, I have a question. So why is it important to study Io's atmosphere during eclipse? I mean, why is this an important thing to understand?
Sure, yeah. So Io heavily contributes to the Jupiter environment, and of course, understanding space environments and how atmospheres react to various eclipses give us a lot of information about other space environments, especially the correlation to Jupiter's magnetosphere and how Io's atmosphere directly feeds the plasma torus. It's really interesting to understand what that atmosphere comes from and why it's changing so much, because Io is one of the more fascinating bodies with all its volcanism and its atmosphere that goes up and down when it goes behind Jupiter. So all this scientific stuff gives us an interesting proxy for other environments.
And do you see any variability like in the torus or in the aurora or anything produced by during the, is there any other variability when Io goes into eclipse other than just its atmosphere collapsing? Does anything else change?
So obviously we know that sublimation would be the only remaining producer of the atmosphere. So we've been studying what happens to the atmosphere. I'm not sure if there are other effects more so than the collapse, but we know that oxygen, for example, doesn't respond to collapse, and all that kind of stuff just sort of adds more to the puzzle of Jupiter's magnetosphere and the interaction with Io.
Okay. Emma, do you have a quick question?
Yeah, so you mentioned that you use Jupiter as a standard candle for these observations. Can you explain a bit more how you do that?
Yeah, so here, we have the spectrum. When Io goes behind Jupiter, the disks are actually very close together, so we get a lot of bleed over from Jupiter into the slit, even though it's not directly pointed at it. So all of this stuff in the background, you can see how most of it's at, for example, this dark blue is at 70 kilorayleigh per angstrom. Most of that is entirely Jupiter. So what we do is we take an image of Jupiter's disk and then scale it and sort of shift it based on the Doppler shift in order to subtract all of that background out. And that gives us the sort of nice residual with only Io remaining.
I see. So you don't use like just a standard Jupiter spectrum or something. You take the observations.
Right. We take a
That's
concurrent one. Yeah.
I was going to say Jupiter is really variable. It's not a very good standard candle, but if you account for that, then that's good.
Right. Thank you.
All right, excellent. Well, thank you, Mikhail. It was an excellent talk.